Okay, so this is the beginning of my tech talk. My name is Katherine Whitlock, and I'm going to be talking about language design and how semantics and syntax work together to form what is known as programming language, and also the parts that make it up besides that. So, it's also known as why brick is a thing, because this is like an explanation to you guys, like why I'm designing this really weird, strange language that you might not be like understanding at all, and like the sort of trials and tribulations I had to go through to get there. All right, so a lot of languages really start out trying to solve this really big, huge problem that's in an industry somewhere or something like that. So we have a bunch of languages. For instance, we have a problem of distributed fault-tolerant systems back in the 90s. There was a problem of having expressive syntax for scripting around that time too. Using small talk objects on top of scripting, simplified concurrency with MapReduce problems, new programming styles on existing platforms, type inference in systems, mathematical purity. These are all problems that a lot of common languages that you actually work with every day try to solve. So Erlang, Python, Ruby, Clojure, Scala, ML, and Haskell. So Erlang is clearly fault tolerant. It was designed for telecom systems. Python and Ruby were both scripting languages created around 1993, 1994, trying to solve a problem that Perl wasn't doing very well. So Clojure was trying to, in 2007, was created by Rich Hickey to solve MapReduce problems and concurrency on a platform that he thought needed a lot of help doing that. And so he created Clojure in order to solve those problems. Scala is functional programming on the JVM. ML is created by actually Milton, who designed, or Milner, sorry, who designed the Hindley-Milner type inference engine. And then Haskell was, because a bunch of math heads got together, was like, we need a new language that actually does what we want. So, yeah. All right. Why is it formatting text like that? That's weird. Okay. So you have this problem. Okay. Somebody throw out a problem that they'd like to see solved in some sort of syntax that, I don't know, they don't have. Okay, I'll go with concurrency, because concurrency is or monadic. Yeah, well, okay, let's do monads. So say we want to implement monads on top of Ruby or something like that. And there isn't a really easy way of expressing monadic syntax, bindings, stuff like that, in Ruby syntax already. One of the ways to solve that sort of problem is by using something called a domain-specific language, or a DSL. And what a domain-specific language does is it attempts to build on top of a language that you already have, some sort of syntax and grammar rules that you already have, in order to extend it to do what you want. A really good example of this is using Lisps, like Common Lisp and Clojure, where syntax is simply new forms of the language itself. And so you can create macros, which are compile time, runtime, substituted forms in the language, to create new expressions that actually allow you to define things in different ways. But so yes, DSLs are great. But what if our problem is too big? We can't just solve like so we can do monads in Ruby using a DSL. We can define operators and stuff like that override certain things. And that's great and all. But what if we have something bigger? What if we solve a bigger problem like I really like distributed systems, because distributed systems are a really big problem right now. So if we're trying to solve like the problem of distributed languages and how we're going to interact with processors, or like scaling to thousands of processors across a giant system or something like that, well then a DSL is not really going to work all that well. So these are languages that DSLs can be built on fairly easily. So your problem's too big. So it can't be a DSL. It's got to be a standalone language. So that's what I came up with Brick. Brick was designed, from my perspective, to make concurrency easier to people who don't understand it, functional programming easier to people who don't understand functional programming in an object-oriented setting, though, and stuff like that. So I was like, Haskell looks too weird. It has too many symbols. You use this $sign over the place to like force evaluation on the right-hand side that gets passed into the left-hand side. ML is very outdated. It uses Pascal syntax from the 60s. And it looks really gross because you have keywords all over the place. Python and Ruby are really, really cool. They're syntactically very, very pretty. They have a lot of white space. They make code look nice. And I really, really like that. Scala is really neat in terms of its type system. In fact, it's one of the strongest type systems that's used in production Java applications and stuff like that out in business. And Rust is really nice, but it's a bit too level. You have 4 pointer types. I mean, come on, what's with that? So let's talk a little bit about languages. So you have, as you probably know, declarative languages, and then you have procedural languages. A declarative language is saying how your program works. You're not really telling the computer what to do, you're just saying, okay, I have this algorithm, and it functions like this. Procedural languages, on the other hand, are like telling the processor how things work. And then the two greatest examples of these are Haskell and assembly. Haskell's about as high level as you can get in describing how certain algorithms work, whereas assembly is about as low level as you can get. You're actually defining sequences which then get assembled to bytecode. And so these two paradigms are like the main two things that you can separate things into. There are things that span this. For example, Scala is a pretty good example of something that spans this. OCaml is too. Scala and OCaml attempt to rectify problems of declarative syntax with, you also want to have procedural stuff inside there. So they allow mutability and also Haskell style, like purity. So new languages around right now are trying to hit this really interesting sweet spot. So you have like JavaScript and C#. I don't know why JavaScript's on the safe side. I think there's a few twinges about it that make it kind of weird, but that's all right. So you have JavaScript, C#, and Java, which are pretty high on the safety and productivity scale. I mean, you can get a lot of work done fairly easily and fairly safely inside of them. C++ is over here on the high performance, but not too high in terms of safety. C++ 98 was even less safe because you didn't have all this the nice auto keyword and all that sort of stuff. Right now, a lot of languages are trying to target this area, the high safety and high performance. I know specifically Rust is probably right here right now. It's not too safe in terms of a type system. It still only does local type inference, which means it can only figure out types inside of a function, not outside of them. So I don't consider it super safe, but it is definitely pretty cool and very performant. There's other languages. This graph is actually designed for a language called M#, which is what Microsoft is working on right now, which is supposed to be a limited, it's a new variant in which they're trying to do type check C++ sort of stuff and C# together like as one, and it's supposed to be really fast, and so they're trying to focus on this point. Brick, my language, is not really edging so much on the performance side. It's more like right here. I'm trying to go highly safe, highly typed, but not as performant. Haskell's about right here. Haskell is very safe. Up here, I should say. Haskell's very safe, but it still fails to like have some of the performance issues that like C has, for example. So you want a language. So we've talked about our DSL, and now you decide, okay, I want a language for describing my distributed application across multiple processors. So what's your platform? This is really the first question you're going to ask yourself. Like, am I compiling for JVM, CLR, x86 assembly? Am I going on a custom VM that I'm going to write myself, like, I don't know, Rubinius, or are we going to work on PyPy or mruby or CPython or something like that, or are we going to write something? So that's really the first question you have to ask yourself, because this question will define everything about your language later. If you're targeting x86-64, what are you going to use as a backend? I'm personally using the LLVM, but there are other systems out there. There's like C++, there's intermediaries. You can work with GCC, you can work with Gimple, I think is the intermediate language for GCC. You can work with that, you can develop that and get GCC to output your binary from that. But you could also work with like the JVM and CLR. I haven't worked with these two platforms myself, but I've heard very good things about how easy it is to hook into the CLR's backend and actually run your code on it. So apparently it's a fairly good platform. There's a language called Cobra, which you might want to look into later because it's really cool. That runs on the CLR and does a lot of really cool things with it. In fact, I might show it off. The next question you really get. So we've decided on platform. Let's say we're going to go on the CLR, because Scala already runs on the JVM, and the CLR is pretty cool. And we're scaling to a CLR instance that's running across thousands of processors. So what's our syntax going to be like? We can use, I don't know, Python, Algol, Pascal, Lisp syntax maybe, like Clojure decided to do for extensibility. This, once we've decided on our platform, this sort of shapes how it looks. So you have to recognize that a developer, probably you, but also other people, are going to be spending tens, if not tens of hundreds of hours working on syntax and figuring out how it's going to work together, and then thousands of hours working in the syntax itself. So when you're designing a syntax for your language, you want to keep it clean, simple, easy. You want to make your life easy in terms of writing the system that interprets it, that understands it. You want to keep it simplistic if you can. Lisp is about as bare bones as you can get. It's just parentheses with a bunch of rules inside of it. So like if you're writing a Lisp interpreter, you basically, there's tons of resources out on the web, and it's just like, I can copy and paste regexes into my Lexer, and it's done for me. So, but doing stuff like algol syntax or Pascal syntax can be a little iffy at times. Examples of these: OCaml, StandardML, Pascal, Delphi, C, C++, Rust, Java, C#, Lisp, Common Lisp scheme, Clojure, also Key, and then Python, Ruby, all those. Okay, so we got some syntax down here. We're gonna use Pascal because everybody loves Pascal syntax, right? Yeah. So we're gonna use Pascal syntax because it's easy to parse, and our application is running on the CLR. So now we have the CLR, we have Pascal syntax, we have a type system. The type system is what goes through your program and figures out, okay, so I've got an integer here, and I've got a variable here. That variable is clearly an integer because it's assigned. So we can just say that's an integer from now on. And then when you use that variable later on, it can say, okay, wherever I'm using this variable, everything that I'm using in it should be, or is supposed to be, an integer. And it keeps track of discrepancies and things like that. You can have a dynamic or a static type system. So a good example of a dynamic type system is something like Ruby and Python, where it's actually duck typed, but that isn't really the best definition. Basically what it says is, until you send the message, like for your function, you don't actually know if it's going to get responded to. Whereas a static type system is resolved at compile time, so you know all the types when you're compiling. You can either be strong or it can be weak. Actually, all dynamic type systems are by definition strong. There's actually only 1 or 2 examples that I know of a weak type system on a dynamic language, and that's actually versions of BASIC back in the 60s, where you could actually write to memory addresses and destroy your system in the process. So that's why you don't have a weak type system on a dynamic language, because you get these weird problems that can arise very easily. Lisp is a strong typed on a dynamic system. Python and Ruby are like that too. But when you're working in a static language like C, C++, Rust, you have the option of choosing between strong or weak, or even strong with loopholes, which allows you to do unsafe things in a lower level language and then hook them into your language as it were. OCaml is strong with loopholes, meaning you can write like functions in C that you then hook into an OCaml, and OCaml can't really determine the type. A good example of this is actually the serialization deserialization library, because you can serialize out to a string, but when you deserialize back in from a string, OCaml has no idea what sort of type that is. It's just like, this was a string, what's it supposed to be now? And so you have to provide that information. And that providing that information can actually make it so that you can actually take like a string that's supposed to be an object and say, no, this isn't an object, this is an integer, and it'll blow up in your face when you try to use it later. So dispatch is the idea of disseminating your function calls throughout your language. I talked about Python and Ruby a little bit. They have a dynamic dispatch, which means that they aren't resolved until you run them. Static dispatch is what C++ by default, and C, and Rust, and Java use. Yes. I think Java uses static until, okay. So typically, when you're using a static dispatch system, your objects, if they are known at compile time what type they are, the method calls on them will actually be resolved, meaning that we can figure out, we can trace the path to how we're calling the functions. In a dynamic dispatch, for example, okay, let's say we have a superclass and a subclass, right? So some parent and some child classes, they're linked by inheritance. In Java, if you define a method on the superclass, and then redefine that method on the subclass, and you call that method by creating a new variable that is the subclass, it doesn't know whether to resolve that method call to the subclass or the superclass, because it doesn't know about the type information until you actually run the program. because your object could either be of type child or type parent. And so that increases, that introduces an overhead that is a little annoying. Or it could be both, which is what C++ and Java actually do, where we have static if we can, dynamic if we can't. Dynamic calls can result in runtime errors if they aren't fulfilled properly, and that's where some runtime errors come from. Memory management is a big issue, so you probably all use garbage collected languages. Garbage collection is a big thing back like now. Garbage collection was originally invented with Lisp. So Lisp originally had a stop the world garbage collector. I should just bring up. It stopped the world garbage collector, and it was used because what would happen in Lisp is you would spawn a bunch of cons pairs, a bunch of memory cells that would link to other memory cells. And then they would get copied if you were creating a new version of the list, and the old ones would just be floating around in memory somewhere. And that wasn't good because we had to know where they were and deallocate them safely so we could use that memory again. And so the creator of Lisp, whose name I'm blanking on right now, but I do know, actually designed this garbage collection system that would go through memory, keep track of where things were, and then deallocate them when it needed to. There's also scope-restricted memory management, which is what Rust is doing, which is really, really cool because what it says is, okay, we're creating new variables in this scope. As soon as we exit this scope, we can just deallocate those variables in the order they were allocated. So we have no need of keeping track of them or anything like that. Rust is actually removing the garbage collected pointer type. Yay! So we don't have that anymore. It's been deprecated as of 0.9. And that's good because everybody's using the scope restricted one because it's safer and it's better, and the garbage collected one was having a bit of issues. So types of garbage collection are generational, which means we garbage collect the newest objects first, stop the world, which just keeps track of everything, and then stops the entire runtime when we need to collect memory. This is what Java was until about 2006. We can have incremental, which is in little tiny slices of time, we'll run our garbage collector and collect what we can. And then we can have hybrid. Java's an incremental system now. It allows it to be very fast on things that require real-time systems. So you can actually run Java on like 32-bit microprocessors and stuff like that. And for applications like that, an incremental garbage collector is very important because you can't stop for long periods of time. If you're running inside of an airplane, you can't suddenly stop the processor and be like, I'm not accepting input anymore. Ha ha ha! Because then your airplane will crash, and that's a problem. So, yeah. Next sort of thing is about concurrency. So we've done memory management, syntax, dispatch, and type system. And now we're getting into concurrency, which is the problem that we were trying to solve. So we're trying to solve this problem of concurrency on multiple threads, multiple processors at one time. How do you sort of do that? Clojure is a very good example of trying to solve the concurrency problem in the modern day world. So back when C++ was designed, the main way of dealing with concurrency and problems like that was to use mutual exclusions and locks and semaphores and messages between different threads in order to tell them, oh, I'm done using this part of memory, you can use it now. As we go forward, we're trying to model in mathematics more and more how to represent these sort of ways of dealing with shared memory in a pure form. So there's actually a thing called the join calculus, which is one thing, and then we also have something called pi calculus, which is another way of describing concurrency in a mathematical sense. So we can use lock mutexes and semaphores like C++. Or we could use something like shared transactional memory, which is what Clojure does. And so Clojure says, okay, I'm going to keep a list of history of this one object. So I'm going to create this object, and when we modify it, we're going to make that change atomic, the way actually a database does. Rich was a database. We worked on databases before he designed Clojure. And so we're going to make that transaction atomic. So if we try and do multiple transactions on the same object at once, and it fails, we'll immediately roll back in history to the object state where we were before, and then we'll just try the transaction again. And what that allows you to do is just throw changes at an object without any care, and if something tries and accesses it, you don't have to worry too much about the problems. And so that's really cool, and that's actually what I'm going to be using for Brick, is I'm going to be using a shared transactional memory system, probably coupled with channels and or the actor model, which are other ways of solving this. For our language, our theoretical language they're talking about now, let's talk about the actor model. So Erlang uses an actor model, which is where we spawn little tiny workers that are your actors. And they communicate between each other using some sort of message passing system. They can use channels if they want to, or they can use something lighter. And so in this actor model, we have thousands upon thousands of actors. And the cool thing is you can multiplex them across multiple processors. And so if we use an actor on one processor that performs a locking action, we can actually move the other actors that were on that processor to another processor. And so it allows for very high scalability in terms of workloads across multiple processors and threads and stuff. So that's really cool. I really like the actor model. I think it's really cool. It's a little bit of a trouble trying to integrate it with this. There's actually a really cool Scala library called akka, which I know they work with inside of Concurrent, I think. Concurrent and distributed, yeah. And they use that on Java, but it's much better on Scala. But they have a really cool shared transactional memory actor system, which they call transactors. That's what it was. And it's pretty neat. I encourage you to look it up if you're interested. So we have concurrency, syntax, dispatch, memory control, and a bunch of other stuff. So we basically defined how our runtime is going to work. Now we just have to code it. So runtime typically has stuff like basic class library support, so all of your built-in libraries, stuff like that. Thread support, so our concurrency. Type checking, type inference, stuff like that. Security, so we don't want to access memory that's being accessed by something else without throwing an exception, because that's bad. The COM marshal, this is the CLR. I don't deal with COM files or COM systems on Windows. I haven't really heard of them much at all. But you have your exception manager, which deals with unwinding the stack when you throw an exception. And the debug engine. And then you have your Silva native, code manager, and then the garbage collector we were talking about. So, over top of class loader, which will load up your class files. So this is a basic run. Actually, this is a pretty comprehensive runtime. A basic runtime would be something like debug engine, security, class loader, and maybe a little bit of a class library on top, and that'd be it. There's actually a language that's being developed out there called Luna, and that's basically all it has right now. Is you have 3 primitive types, and you can spawn threads, and it fork joins, and that's it. And that's basically all it does. But it's really cool. So it has a very minimal. Its VM is less than 5,000 lines of C code, which is pretty impressive. But so yeah. Okay. So we've gone through this whole spiel about how languages are formed and sort of what goes into them and what sort of things you have to take into consideration and things like that. So where's Brick? As you probably know a lot, Brick is the language that I'm designing. I've put around more hours than I care to think about into this project. Lots of research, as you can tell by my presentation so far. This is all stuff I learned in trying to research how Brick would come to be and how it would come, how stuff would form. The concurrency especially, because I didn't know anything about concurrent models before January, and then I started reading everything I could. So most tokens are defined. So I have a syntax. I have function as a method, class, trait. It uses trait-based inheritance, which is something I can get into later if you want to if we can talk about that. I have ways of defining the Lexer and in regular expressions and stuff like that. Syntax for integers and floats and string literals and multi-line string literals and blah, 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 all that sort of stuff. I'm working on the parser right now. Previously, I was using C++, and I was using a handwritten Lexer because I thought I would have to. And then I was using what's also known as Bison, which is a parser generator for C++. The problem with Bison is it's not terribly well documented, and I was using parts of it that are very, very new, which, because traditionally what you do is you create a union, which is this thing that can take up a memory of the longest thing that you have inside of it. But using the new version of Bison, you can actually allocate C++ objects correctly, which is nice. So you can actually have an object-oriented parser, which is really, really good. And I was like, okay, that's really cool. I want to try that. So I got that working. But then I decided C++ was more effort than it was worth. Doing all the memory management and all that sort of stuff was just a right pain in the ass, if I could say so. So I'm switching back to what I was originally trying to do, which is NoCamel. And I actually just fixed the Lexer today, so that's working, which I'm really, really excited about. I'm using the LLVM, what was originally called the low-level virtual machine. Really is not a virtual machine anymore. It's really just a name that isn't even an acronym. But it's a big framework that allows you to create syntax tree nodes and define how they get turned into what's known as the LLVM code gen, which is these things that the LLVM takes in and processes. If you want to know more about how the LLVM works, look at my previous compilers talk, because I go into a bit more depth about how that functions. It's written in NoCamel, which is an interesting language to say the least, but I think it's fun. So here's a little taste. This is actually the example I have on the GitHub page right now. There's an entry point into all programs, which is main, the function main. This does not take any arguments, so it actually has type unit as the input, but so we don't need anything there. A let form is for creating variable bindings, so it's very functional in that way that you cannot just use a variable. You actually have to have variable declarations, or declared is what they're called. And so nums is an array of 1 and 2, noms is an array of strings, which is Chad, Nick, Kristen, Steve, and odds is another array which is created from mapping this function, which is a lambda, on top of nums. And then I say for each thing in odds, which is an array of 2, we call .each, which isn't the iterator. And then this symbol means that we do a fork on each of the elements that we can, according to the number of processors we have, or threads that we can execute. We have a thread limit that's actually, so there's a thread limit and then there's a green thread limit, and this spawns green threads, so that actually get multiplexed across the threads, which is pretty cool. And that runs, this is another lambda, which takes a num and then prints out some sort of string. And so that's my example that I've had up for like 3 or 4 months now. I've changed it a little bit here and there. I originally had like a tilde arrow there, but then I decided that the tilde would actually function as the synchronization system for the way Clojure does synchronization. So yeah. So we can talk a little bit more. I'm using invariant types, which is interesting because my type system actually considers traits, classes to be types. So in a lot of languages, types are disparate from object types and class types and all that sort of stuff. But in my language, they are one and the same, which means that the type hierarchy is composed of classes and traits. And what that means is that when we compile, the compiler actually goes through and finds all of the classes that implement a trait, and then creates a variant type based on that at compile time, and inserts it into the tree node, the type tree. So what that allows us to do is do really cool things like this, where we can define an invariant type that has either a leaf or a branch, and then we can create a function inside that type that matches on our current node, which is either a leaf or a branch, because we define those up here. And if it's a leaf, we'll print out the item. And if it's a branch, we'll call ourselves again and we'll recurse on both the left and the right. This is actually syntax sugar that I'm including. It really boils down to something like this, where we define a trait and a function inside that trait, and then it creates classes that are based on that. These are actually not really needed. They're there because if you can actually have, this is the constructor of the class, and you can actually have things in the constructor that are not the same names as the members of your class, but if you do have them the same as the members of the class, then you don't need the members block. That's just there for showing you what it's going to look like. So yeah, that's a bit about language development and design. And I think I'll actually show you Cobra, and I'll show you Luna, and I'll show you the parser that I have built on Yacker. So, time for a little demo, I guess. That's F11. Okay, so back in, this was before the semester ended. Before the semester ended, I started working on the grammars for Brick. Very simple. I'm trying to use an iterative development system, or development process for developing the compiler, which means that I will go through creating a grammar for one form, implementing it, testing it a lot, and then going to the next one. and keep doing that. And that, because traditionally compilers were made so they define the syntax, it's very waterfall design. You have a syntax. In fact, the C++ syntax is like that big. It's a book. You can buy it. And you put your syntax in your Lexer, and you put your grammar in your parser, and then you define your code generation system, and away you go, and you're done. So it's very front to back. Traditional compiler design, or contemporary compiler design is done in a more iterative fashion, where you'll do little tiny bits of the language at one time. And so when I actually was writing this grammar, I started out with a let. I didn't actually have lambda or anything else. It was just let, variable binding, stuff like that. I didn't even have fancy like expression calls that you could bind variables to. But so that's the grammar that I have right now. It's using BNF, which is Buck's now form. But it's really cool. This site called Yacker. It's created in 2005, and it's on w3.com. What it allows you to do is define the BNF, and also the terminal symbols at the bottom, and then give it some text. So I can say like, I think I have explicit validate text. So there's no plus, excuse me. And so what it does is it creates a parse tree. It's LALR, which means it recurses to the left. And it uses a look ahead. And it creates a syntax tree representation. Not an abstract syntax tree, because an abstract syntax tree is compressed, but an actual syntax tree.
And this is for your length?
This is for Brick.
Okay, cool.
So this is the binding form. So you can see it actually parses. It is parsable. It is a thing. It works. In fact, one of the cool things about this tool is that you can actually generate valid text. And so if I pretty this a little bit more, because it doesn't really look like anything right now. This is not valid. This would not compile theoretically, but it is syntactically valid. Which means that the parser would accept it. The compiler wouldn't even come close though. And basically, so this setup here says we have a let form with two variables bound, one of which is a reference and has type TSN, which is equal to 76. And every time we access tot, we call the function CFUX. That should actually be like this, but whatever. I have to fix that in the grammar. And then we also have for the ENWG variable, we have a lambda that is called at a later point. It's called future. And it takes one parameter, which is a reference, and another parameter, which is not a reference, and the reference is of type goo, and it returns 66. So it doesn't really do anything with those variables, but it still returns 66. And then at the end of the like form, we call QXXX, apparently. So that's one of the cool, I think that's really cool, that this tool can like generate valid code that is not really valid, but is kind of valid. So that's the parser. Let's look at Cobra. I'll show Cobra. This is Cobra. This is the language I was talking about earlier. It runs on the CLR. It uses Python syntax, but you also have first-class testing and code guards, which is really, really, really neat. It's very clean in terms of software engineering principles and stuff like that. It is both static and dynamic binding, and it is compiled performance. So it is compiled, and then it runs on the CLR. So, yeah, I just wanted to show you that. And then Luna is this. So it's less than 2,000 lines of code at this point. It only has the Lexer, the parser, the test suite, and an AST, and it uses the line noise for REPL integration with the command line. But it looks like this. So you have like some function that has greet that takes a string and returns hello plus name, and so it can figure out that this is a string from the fact that you're giving it a string. And here's an explicit example. So here you're explicitly stating that I return a string. You can overload functions. It plans to have multiple dispatch, just like I plan to have multiple dispatch, and I plan to have a lot of things, but haven't really gotten around to doing it yet. But yeah, there's some syntax sugar for calling methods. For instance, this is sort of like passing things into one another, which is nice, and that's sort of where I got some of the object-oriented ideas for Brick, because it's not really object-oriented, it's more type-based, but similar. And then they have a fork join system, which allows you to call commands on the command line and then join across them. So if you're interested in language development, you should check out Luna because it's really small and you can read through the code base in a night sort of thing. So, yeah. All right. So at this point, nobody's really been like raising their hand or talking or anything. So I'm going to ask you guys, what sort of questions do you have for me? This is what I do. So if you have any questions about language development or language design, ask them, please. Like, what do you want to know?
So, for building Brick, at least, did you like have like in like from the very beginning like certain ideas as far as how large is Brick right now even like as far as like code base get?
It's pretty small.
No.
It's like a couple hundred lines of code, not a couple hundred, more like 400 lines of code. Do you want to see it? I'm going to show it. So the Lexer looks like this, and it defines a bunch of syntax rules for like parsing integers and stuff like that. And then I have a bunch of rules for how we actually emit tokens from the Lexer. These are the tokens, all of these capital things. And then I have a bunch of other stuff. So this is the indent rule. This is actually, this right here is the problem I was trying to deal with before that I didn't really know how to solve because I didn't know NoCamel all that well. But now I solved it pretty easily. And these are other rules for the comments and block comments. The parser is not syntax highlighted, unfortunately. Not all that well, at least. And it looks like this. And this is what the syntax rules are. It currently doesn't work. I broke it this afternoon, but I'm working on fixing it. The problem is that I'm dealing with a lot of list types. You can see list literals all over the place and concatenation operations. So it's having a little trouble resolving how those work. The actual abstract syntax tree, the definition for it at least, looks like this. So we have a bunch of type invariants. So this is like a type expression which has a bunch of constructors. And these constructors actually emit things of that type, but they are distinct. So you can pattern match over them. And so I created a bunch of printing functions for how to print down here, like string of binding, string of call, string of variable, they all pattern match across this sort of stuff. And then there's a driver, and the driver basically says, okay, I've got a file, and then I read this file into like a stream, it parses the stream into the Lexer, and then it passes the output from the Lexer into the parser, actually right here, lexing from channel pi, and that says parser.statement, so that's the first action we do, we call statements. And then it takes the Lexer.indent, which is the first starting rule, and the buffer for the Lexer. And then it tries to print it. Yeah. So it's not all that big right now. A lot of the concurrency stuff, a lot of the memory allocation, garbage collection stuff that I have to do, a lot of that is all done in the runtime, and that's actually going to be separate from this because the runtime, well, while it is part of the compiler, it will be it's like a core library sort of thing, like you saw in the stack. It isn't really what the compiler deals with. The compiler deals with more of like turning this, when I give it, into nodes that it can then attach information to. Yeah. Any other questions? Yeah.
What is the velocity of an unladen swallow?
No taking my question.
Sorry, you weren't getting me. Could you do that again?
Okay, well, it depends on whether it's an African or a European swallow.
Okay, I've got a real one. I may have just missed this at the beginning. How long did it take you to develop this? How long have you been working on it?
I've been working on this for about 5 or 6 months. Jake, what do you think?
You started in September.
Like September-ish. So, about that long.
What kind of knowledge did you need coming into this to get started? In general, don't enumerate.
Not really any knowledge, more of the drive to learn.
Okay.
Like,
So you kind of approached it with nothing and learned it as you went?
Yeah. As I've got deeper and deeper into the subject, I've kind of discovered I really like this sort of stuff. And so I'm probably going to end up trying to do something with it in the future. I don't know, maybe a master's degree or something like that. But yeah. So everything I've learned so far. And I think I've learned a bit. I haven't learned all there is to it, not nearly enough. I want to learn more about it because things like concurrency go right over my head. Like there's some stuff in there that's really complex. So yeah, I'm still learning.
Product though. That's awesome.
Yeah.
What's been your favorite part of developing Brick?
All the problems. Because the problems make you think, and thinking makes you learn. And so, okay, I came into this expecting, oh, yeah, object-oriented design and functional. That totally works together, right? And as I keep going forward, I discovered that there's more and more stuff that's sort of different about the two. Functional programming by design, actually, as you can see here in the AST file, sort of tends to make it so that you define types, and then you define functions that deal with those types, as opposed to creating an object which has the type information and the associated information about it all contained together. And so trying to figure out ways of reconciling those two principles has been a real challenge and a lot of fun. The trait system, which is just the syntax trigger stuff, is pretty cool. But I really like traits and like how they work. They're basically interfaces with default implementation. So in case you were wondering, that's what Java 8 is adding is traits. So yeah, I think that's been my favorite part. Learning about concurrency, learning about shared transactional memory and how it actually works and how atomic transactions work between history and sub-objects and stuff like that. That's really cool. Yeah.
Cool.
Any other questions? Any other topics?
Besides the parse tree web tool that you showed before, are there any other cool tools or technologies or things that you've learned or is useful for making a language?
Yeah. Knowing regex really well is very helpful. You don't have to know it terribly well. You don't have to know there's a library out there called Anagrama, and it has a lot of really special stuff in it. You don't have to know it to that high level. You should know about optional parts of regexes and how you can have the star is different from the plus and stuff like that. You don't really have things like groupings. You can't just grab because your entire thing is grabbing. It's matching. So stuff like that. Regexes are very helpful. Knowing how to read a backwards now form, a BNF, like the one I had up there originally, is very, very helpful. It's not stuff that you can't learn though. You can definitely go into it not knowing all that stuff and definitely come out of it learning more. Knowing how to properly resolve your shift-reduce conflicts when you're trying to deal with an LR parser is very helpful. Basically, it involves creating new parse rules in order to resolve those, stuff like that. So yeah. Anything else? Thumbs up? Good talk? Okay, cool. Yeah. All right then.